Hi everyone. In this video, I'm going to talk through the workflow for the Abalone dataset. The goal here is a regression problem. We use the Abalone's physical measurements to predict the rings, which is used as the age. I will quickly go over the main pre-processing step, explain why the model size it used make sense for this dataset, and then talk about what the result might mean in the real world use. So first, it loads the dataset from UCI repository using the fetch function. Then it sets the X to be the features and Y to be the target. From the variables table, you can see here, the X is a category and everything else is continuous, like length, diameter, height, and several weights measurements. And again, our target is rings. Now, next, it do some quickly sanity checks. Um, Here, the dataset has four, four 4,177 rows and 8 features. There are no missing value here, and it also doesn't see any duplications, which is nice because it means we don't need to do extra cleanup. It also checks the number of unique value. The sex has 3 categories, and the numerical feature has lots of unique values. So it's clearly a mix of categoric and continuous variables. Then it combines the X and Y into one data frame and um, and generate lots of plots here. So we will quickly go through it. So, by reviewing these distribution plots like histograms, box plot, and probability plots, a lot of the weight variables are right screw. You can see also you can also see outliers in few places. Mm, and here, oh, okay, the violin plot makes this really obvious, especially for height, where there is a long tail and some extreme points. And over here on the uh, ring distribution plot, most samples are in the middle range, and there are fewer samples at very low or very high rings. That matters because models usually perform worse on those real extreme values. Mm, Next, it checks the relationships between variables. The heat map show a lot of these size and weight features are strongly correlated, like length and diameter, and also the different weight measurements. So we are dealing with multi-collinearity, which is one reason why a regularized linear model like Redoge can be helpful. Okay, here we need to focus on the target. It computes the screwness with Y screw here, and the rings has a positive screw about 1.11, which confirms it's the right screw and has a long tail. To reduce the impact of extreme value, it used IQR-based rules to flag very extreme rings value, and then it removes those rows from both X and Y. After that, it plots a box plot of rings again, just to double check that things looks more stable. Now for modeling, it created a holdout split using trend test split with an 80 to 20 split here, and set a random seed so it's reproducible. One really important thing here is make sure you split first and only then do any scaling, because if you scale before splitting, you risk data leakage. So it use the standard scaler to fit it on X train only, and then transform both X train and X text. So it can also scale Y for uh, models like SVR and MPL, and later transform prediction back to the original scale before evaluating. So to get a to get a sense of which features matters most, is trained a random forest regressor and plot feature importance. The random forest works well here because this is structured Tableau data, and it can capture nonlinear patterns and feature interactions without much manual feature engineering. So from the importance plot, we can see share weight comes out as the most important feature, and followed by other weight related variables, and the sex has the smallest contribution. And if we talk about the PyCaret is a great fit for this kind of Tableau regression because it can automate the full workflow, pre-processing, comparing lots of modeling, and doing cross validation and tuning. In this notebook, it's basically doing similar things manually by looping through multiple baseline regressor and comparing their performance on the holdout set. And finally, it evaluates the models using MSE, MAE, and R-square. And it also plot the predictions where vs actuals. So in this result, the strongest baseline are multiple linear regression, with around MACE around 5.1 and Oscar to 0.53. And KN here and are very close, but slightly worse. And this the district decision tree performs the worst, which makes sense because a single constrained tree often overfits and doesn't generalize well. And in the prediction vs actual plot, there is a clear pattern. The models tend to overpredict small rings counts and underpredict large ring counts. That's mainly because rings has a long tail distribution and extreme value are rare. So the model gets put towards the middle. And also, the maximum error here can look really large because it's a percentage error, and when the actual value is small, the percentage can blow up easily. So for real world use, the main takeaway is if we want to estimate age using this kind of model, weight related feature, especially share weight, are the most useful signals. So measuring those accurately matters. But predicting very old abalones is harder, and um, improving that would probably require more high risk data and maybe more advanced modeling. So that's all. Thank you.